Hey man. Welcome back. Today, we are going to do something really cool. We are going to stop looking at databases like they are magic black boxes. And we are going to look directly at the physical hard drive. I want to show you exactly how a database saves your data. You might think database software is incredibly complex. But at its core, a database is literally just a text file. In fact, if you look at the screen, we can build a fully functioning database using just 2 lines of bash code. It's crazy. Look at the db set function. The code says echo string 1, string 2. And use the double arrows to append it into a file called database. That's it. To write data, we literally just add a new line of text to the very bottom of a file. But wait. If we only ever append text to the bottom of the file, what happens when a user changes their password? We don't go back up and edit the old line. We just write a brand new line at the bottom with the new password. This is called an append-only log. Because we never overwrite data. There are multiple passwords in the file. So, how do we read the correct one? Look at the db-get function. It uses grep to search the file. And then uses the tail command to grab the very last matching line. Because the file is ordered by time, the very last line at the bottom of the file is guaranteed to be the most recent update. Appending data to a file like this is incredibly fast, and forms the foundation of massive enterprise databases. Okay. So writing data by appending to a file is lightning fast. But reading data is a massive problem. Think about how that db-get function works. Every time you ask for a user, the computer has to start at the very top of the file and read every single line, scanning downwards until it finds the match. In computer science, we call this O of n time complexity. If you have 10 million users, reading the file takes twice as long as having 5 million users. If you have to read a massive book page by page every time you want to find a word, your system will crash from the pressure. To fix this terrible search speed, real databases use an index. Think of an index exactly like the index at the back of a textbook. It tells you exactly what page a word is on. The simplest type of index is called a hash index. To make this work, the database creates a dictionary, or a hash map, inside the server's ultra-fast RAM memory. As you can see in the diagram, this dictionary maps the user's ID key directly to a byte offset. A byte offset is the exact physical location on the hard drive where that data lives. Now, when someone searches for user 123, the database checks the RAM dictionary in an instant. The dictionary says, go directly to byte 64. 000 on the hard drive. The hard drive skips the rest of the file and teleports directly to that byte, reads the data, and returns it to the user. We just turned an agonizing, slow search into a blazing fast O of 1 operation. But there is a major logical flaw in this design. We are constantly appending data, and we never delete the old lines. If a highly active user updates their profile 100 times a day, we append 100 new lines to the file. If we run this system for a year, our hard drive will fill up entirely with useless old data, and our servers will crash. To solve this, databases do not use one giant file. They break the log into smaller files called segments. When a segment reaches a certain size, say 100 megabytes, the database closes it and starts writing to a new segment. Meanwhile, a background thread wakes up and starts a process called compaction. Compaction reads the old segment, identifies all the old, overwritten duplicate keys, throws them in the trash, and writes only the newest values into a brand new, beautifully clean, tiny segment file. It merges the data to save space without ever interrupting the live users. But what happens if a user wants to permanently delete their account? Remember, we are not allowed to go back and edit or erase lines in an append-only file. So, to delete an account, we simply append a special deletion record to the bottom of the log. In the industry, this is called a tombstone. When the background compaction process runs next week, it sees the tombstone, realizes the account is dead, and permanently erases all previous history of that key from the hard drive. At this point, a lot of developers get very confused. They ask, why are we doing all this crazy work? Why do we append data, create segments, run background compactions, and use tombstones? Wouldn't it be a million times easier to just find the data on the hard drive and overwrite it in place? It sounds easier, but append-only logs win for three massive reasons. First, is raw physical speed. Whether you are using an old magnetic spinning hard drive or a modern solid-state drive, sequential writes are incredibly fast. Overwriting random spots on a disk forces the hardware to do expensive seeking operations, which destroys performance. Second, is crash recovery. If your server loses power halfway through overwriting a file, that file is corrupted forever. Half the old data is mixed with half the new data. With append-only logs, the old files are completely immutable and safe. If a crash happens, you only lose the last few bytes you were appending. And third, concurrency. Because the old segment files never change, thousands of users can safely read from them simultaneously without needing expensive locks or experiencing race conditions. So, the hash index model is incredible. But does anyone actually use it? The answer is absolutely yes. This exact architecture is the default storage engine for a popular distributed database called Riak. The engine is called Bitcask. Bitcask is perfect for heavy write workloads where the keys don't change often. For example, if you are building YouTube, and you need to track the view count on cat videos, every time someone watches the video, you update the same exact key. Bitcask handles this beautifully. But there are two major limitations you must know about before you use it in production. First, because the hash map dictionary must live entirely in the RAM memory, you are limited by your hardware. If you have 10 billion unique keys, the dictionary will become so massive it will exceed your RAM, and your server will crash. Second, hash indexes are terrible at range queries. If you want to find all users whose ID is between 10 and 50, the hash map cannot help you. You literally have to search the dictionary 50 separate times. To solve these problems, we need a different data structure, which we will explore in the next chapter. Keep studying hard, and I'll catch you guys later.